All right, in this video, we're going to look at some more formulas. Since we just talked about percent composition or percent mass, where you can figure out when I have a formula what the percentage of those elements in that formula are. And remember we talked about, or you should have looked at, that all those percentages always stay the same. So CH4 is always going to have the same percentage of H and always the same percentage of C. So now we're going to kind of go backwards, and I'm going to give you the percentages of the percent composition or percent mass, and you're going to figure out the formula. Well, there are actually two types of formulas. There are empirical formulas, and then there are molecular formulas. So we're going to start out with empiricals. And again, we're going to use these percent masses that never change for a certain compound to figure out what these formulas actually are, because those are what we're using. Things like H2O or CH4. Okay, so we're just going to start off with what an empirical formula is. And an empirical formula is the smallest whole number ratio of elements. So it's going to be something like H2O, okay, whereas I have two H's to every one O. That's as much as that can be reduced, okay. I can have something like CH, and that's as much as that can be reduced, but I couldn't have something like C2H2 because I could reduce that again. That would not be an empirical formula, okay. The reason we have to deal with these smallest whole number ratios is because you cannot express a formula in percentages or in decimals. There are always an even number of atoms of one to an even number of atoms of the other. Meaning I don't have 2.5 to 1, I don't have 3.23 to 2, okay, they're always these whole numbers. So we use math, okay, to kind of change these percentages that we're going to look at, or grams that we're going to look at, or parts of moles that we're going to look at, to actually then make them into whole numbers. Because that's really what it boils down to. The moles may not be an even number, but the number of atoms of one, the number of atoms of the other is always even. You're not splitting the atom apart to make these formulas. I have an even number of 2 H atoms to 1 O atom. I don't have 2.5 or 2.32 or something weird, even though I might have that number of moles, because I can have decimals of moles because moles represent so many atoms. Just like you can have parts of dozens, I can have parts of moles. So we're taking these parts of mole numbers, using a little bit of math to kind of whittle them down and get our actual ratio in whole numbers for the atoms. All right, well, when we look at these empirical formulas, okay, we're always going to assume that we have 100 grams because we're going to use our percent compositions, because those never change for that particular formula. So we're going to use these percentages, and we're going to assume that we have 100 grams of that particular total compound, because then I can just say, okay, well, if I have a compound that is 50% C and 50% H, and if I assume that I have 100 grams, that means I have 50 grams of C and 50 grams of H. We're just kind of changing our percentages into grams. So that's why those are straight up equal when we look at these problems. When we talk about converting a percent into a gram, they're equal, because I'm going to assume that I have 100 grams so that I can make it equal. Because if I have a percentage, I can assume I have any number of grams of this compound. It's just easiest to assume that I have 100 because then they are equal. So we're going to look at this little rhyme to kind of remember what we have to do to make these empirical formulas, or to kind of mold our numbers into these whole number ratios of these atoms. And it goes like this. It goes with percent to mass, mass to mole. You divide by the smallest, and you multiply till whole. And what that means is that we take our percentages that they give us. So say if I have 5% C and 95% H, okay, that means I'm going to make that into a mass. I'm going to go 5 grams of C. I'm going to go 95 grams of H, because I'm going to assume that I have 100 grams. So I just have the percentage is my grams. I'm going to go mass to mole, because these are always whole number ratios and mole ratios. Okay, to get my atoms, I'm going to make it a mole ratio, okay, because the mole stands for so many atoms. So what you do is you divide by your molar mass, look up the molar mass for each one, okay, and whatever these numbers come out I pick the smaller of the number and divide by it, because what's going to happen there is I'm going to make one of them 1, because if you divide by itself, it's going to be 1. The other one should then fall into place to be a whole number of some sort. And depending on your numbers, they may not be exactly 5. It might say 4.998. Well, that's essentially 5. Okay? or I might say 2.952, well, that's essentially 3. All right. Now, if you do get one of these to come out to be, these aren't going to actually work out, so you don't want to actually do the math. But say that when I work out one of these, okay, I get this to be 1.5, and I get that to be 1. Well, that's not really a whole number, but it is actually rounding to a fraction. So when you have a whole fraction number that you can make a whole number, we leave it at that. You can't round 1.5 up to 2. That's not close enough. 1.5 is actually 3 halves. And there's actually 3 halves. I can make that a whole number. Well, how do you make that a whole number? Well, you multiply by 2. I multiply by 2, I'm going to get 3. Well, if I do what I do to one, I have to do to the other. So I've got to multiply this one by 2 and have 2. So that'd be C3H2 would be my formula. Okay? Because you can't just round those numbers that are in between up to something, the next highest digit or the next lowest if you round down. These should come out to be whole numbers, or very close to whole numbers, if not a very readily recognizable fraction like a half or a quarter or a third. Okay, you'll see these numbers and go, okay, I can't round that up, that's not close enough. So let's go ahead and try an example together. Okay, so that compound contains 50.09% copper, 16.27% phosphorus, and 33.63% oxygen. What is the empirical formula of this compound? Okay, so I've got 50.09% of copper, I'm going to Cu. I have 16.27% of phosphorus, and I've got 33.63% of oxygen. And I don't know why my airliner here is changing colors, but just go with it. Ignore the color change. So what I'm going to do now is go from percent to mass. I'm going to assume that I have 100 grams to make my percentages just be equal to the gram number. So I'm going to go with 50.09 grams of copper, 16.27 grams of phosphorus, and then 33.63 grams of oxygen. Now I have my percentages. To get my whole number ratios, I got to get it out of grams and into moles, because mole is like the common unit here. Okay, I need to know how many moles of each one. The grams of each one are not really related, because the grams of one can mean a lot less moles than the grams of another. So I want to divide by my molar mass of each one. So go ahead and look up on the periodic table. I'll find copper. It'll tell me that copper is 63.55 grams per mole. So I've got just under a mole. I've got 0.788 moles. Now it is important that you actually leave at least probably 3 decimal places here, so that when you go ahead and divide by your smallest, your numbers will round a lot nicer. You can't be rounding in the middle, it'll throw off your numbers. So you usually need at least 3 places. See how we started here with 4 total significant figures? You probably want to have 3 or 4 digits then when you get your answers with these mole numbers. So now I've got 16.27 grams of phosphorus, and I'm going to divide by the molar mass, which is 30.97, and I'm going to get about half of a mole, so 0.525 moles. I take 33.63 grams of oxygen, divide by 16, and I'm going to get 2.102 moles. Now I pick and divide by my smallest one, okay, because that one then I'm going to make 1, and all the rest of them should then be a multiple of the other. I'm going to divide all of them by my smallest, which is 0.525. So I'm going to kind of go further down the page here. So I would take 0.788 divided by 0.525, and I'm going to take 0.525 divided by 0.525, and then I'm going to take 2.102 divided by 0.525, and I should get some whole numbers, or at least fractions that I can readily recognize. Well, when I divide the first one, it comes out to be 1.5, so I leave that there. I can't round that up. This one is obviously 1, and this one is going to actually be 4. Well, I can't put 1.5 in my answer, so I have to manipulate this number to make it a whole number. Well, 1.5 is the same thing as 3 halves, so all I got to do to get rid of this 2 in the bottom is multiply them all by 2. And so I'm going to have 3, 2, and 8. So I'm going to have Cu3, P2, O, 8. And that is my empirical formula. All right, molecular formulas then are kind of like the next step here. Okay, a molecular formula will actually tell you the number of elements in that particular molecule, which is different than an empirical, because I can have a few different molecules that have the same empirical or the same basic ratio, but since they have different numbers of atoms actually bonded together, it makes them different. So these will tell you the actual number of elements in that molecule, okay? But they are always a whole number ratio, or whole number multiple, I guess I should say, of your empirical. There's some numbers bigger than that a lot of times, okay? So you can have two different molecules or molecular formulas for the same empirical, all right? And the way you can tell them apart then is that their molar mass of the molecular is different and is found by experimentation. Meaning somebody in the actual lab report, in an actual lab environment, found this molecule and it found that it had this actual molar mass. So I know, okay, this one is put together a little bit differently than this one, but they had the same basic ratio or same basic kind of amount of each one together. So for example, all right, I can have something like CH. If I add those up, I'm going to have an actual molar mass of 13.02 grams per mole. If I have something like C6H6 and add those all up, I have a molar mass of 78.12. If I divide one by the other, if I take 78.12 divided by 13.02, notice that we get an answer of 6, which makes sense because one is 6 times bigger than the other. I could also have, other than just C6H6, I could have C2H2. I could have C4H4. Okay, those would all have the same empirical formula, but they would all have very different molar masses. So based on the molar mass of the total compound, I can figure out which actual compound it is because these are actually all named differently. Remember, these would be called dicarbon dihydride or hexacarbon hexhydride. Okay, they have different names because they have also different properties. All right, so we can tell them apart by their properties and by their molar mass, but they have the same basic ratio of C to H. Okay, so let's go ahead and look at an example. It says an example contains 68.54% carbon, percentage of hydrogen, and a percentage of oxygen. If your molecular weight, which is also a molar mass, same wording, of a compound is 350.05 grams per mole, what are the empirical and molecular formulas? Okay, this is also kind of how we get many different types of sugars. The sucrose, fructose, dextrose, stuff that you usually learn in biology, are all because they have the same basic structure, but they are put together in different amounts. Okay, so let's look at this example and see what we actually have got here. Grams of carbon, and then I have 8.63 grams of hydrogen, and I've got 22.83 grams of oxygen. And all I do is I took those percentages and turned them into grams because I'm going to assume that I have 100%, because I do. So I assume that I have 100 grams. So I take all these grams, percent to mass, I went mass to mole. I'm going to divide by my molar mass of each one to get my mole number. I'm going to get a mole number here for carbon of 5.707, and then I'm going to get 8.545, and then 1.427. Divide by the smallest, percent to mass, mass to mole, divide by the smallest. So it'll make the bottom one 1 here because it's dividing by itself. I divide this top two, I get 4, and if I divide the middle one, I get 6. So my empirical is C4H6O. I need to know my molecular, and I know that my molecular weighs 350.05, so I need to see how much this weighs. Take 350.05 divided by whatever that guy here weighs. Well, 4 times carbon plus 6 times oxygen, or 6 times hydrogen plus oxygen, it's going to give me 70. I divide by 70.10, and I get 5. So my molecular formula is 5 times bigger than my empirical. So I'm going to have C20H30O5. Because it's going to be 5 times bigger than C4H6O. I take each one of these and multiply them by 5. Okay? So there's my empirical, there's my molecular, and we're done.